So here we are. This is obviously the actual network analyzer component of the this Hewlett Packard 8510B network analyzer. So this is the actual RF section. On the back we have a one of these interesting. So this is, it's one of these D subs that's got coax pins in it, which is kind of interesting. So this interconnect here goes to the actual, I forget what it's called, the IF section basically, or the, it's not the IF section, it's the, basically the test leads, if you will, in any event. So obviously lots and lots of modules, lots and lots of very well labeled everything. Oh cool, it's got little cute little rubber booties on some of these. These all look to be, surprisingly enough, SMC connectors. So I'm not sure if I want to take this apart because I actually have a friend who will definitely get this working and use it, so oh hell with it. I'm not sure how this disassembles. Obviously over here this is A15, the regulator. So I expect these to be individually insulated compartments. You can see here we have these pull handles. So you can see each one of these has this little plastic handle, which is obviously intended to make removing them easy. So this, because it's just the power board, does not have a metal house covering on this side. So obviously, considering the position of these two screws, they have to be going into some sort of aluminium. So I would guess that there's a metal plate here. So that definitely has an edge card. And it's coming out as well. There it goes. Yeah. So we definitely have a big aluminium structure. So this is our voltage regulator card. That's interesting. Look at this. Oops. This transistor seems to be a bit squashed. It is a transistor, is it? Yes, it is. So we've got lots of metal can transistors. I believe these are wet slug tantalums, actually. Or they're certainly, yeah, they look like wet slug tantalums. Those are really expensive capacitors. 1% resistors, some test leads, and one thing you might notice is that this board is just this beautiful gold plating. The board is just, actually it's interesting, there's solder mask on the back side, but the front side is bare and beautifully gold plated. You can also see we have some of these big old axial diode packages, which is quite interesting. It's kind of an interesting board profile. You can see how they use this edge down here, which normally pokes down. And then if we look down in here, she's being upside down, but you can see down in here, oops, sorry, there's your edge connector, and then there's this big, heavy metal bracketry, and then it actually feels like there's a sheet metal EMI gasket on there, which these probably clamp against, and that's what this screw here and that screw there serve to help with. And then down in here you can see you have these little rubber booties over additional connectors, which I would imagine are test points of some sort, but they're all nicely protected with rubber booties. And then you can just see, look at all of the RF cables. It's kind of beautiful. So these are all individually labeled. So this here says A5J1, and this is A5, and that's J1. And on the other end it says W21. which I would imagine, wait, it's A17J4. I guess this is cable W24, and this end says A17J4, and this end, that's amazing. That is just how you build shit like this. You can see I need to do laundry. Every individual cable in here has each end it connects to labeled on the cable using this heat shrink. And that's beautiful. Of course. And you can see here we have all of these cables coming in. They all have a little ferrite on them, and they do a loop through the ferrite. Back here we have, here's the computer interface. Big ass transformer. There's fuses down here. It's not really visible, but back here is a whole bunch of TO, three transistors or power regulators, heat sunk to this metal plate on the back, which has holes drilled in it. So I would guess that this fan pulls air in, and then it's exhausted through those holes, and that cools the thermal regulation circuit, or the power regulators. Let me just plop this back into place. It sits right in these nicely machined slots in this extrusion. There we are. So another thing you might notice is, oops, it's got these holes which I believe give access to internal test points. So these are SMC, which means they have like a push-on spring retention, so you just need a little bit of force. This is A14J4, which is pleasantly labeled. So this is a crystal filter, so this should actually be very interesting. Yeah, anyway, so yeah, IF mixer, test reference IF amplifier, B1 IF mixer, test ref IF amplifier, B2 IF mixer, 19.9 megahertz local oscillator generator, test reference, something detect, can't make out the other thing, clock, and then something under a whole bunch of cables, test ref, sync, detect. I don't really want to pull all these cables out at once just because it's too beautiful. And I'm not totally confident I'd put them all back in the right place, even though they are all labeled. Actually, it looks like orange is coming in from the, I'm not entirely certain. Orange comes in from this DB20 something, and all the yellow cables are the BNC interfaces on the back. So I'm just grabbing and pulling straight up as carefully as possible. Some of these are interesting. I wonder why they have this right angle. So that's A7J4. This is A7. This is A5/A7, interesting. Nothing. Hey, look. I guess this is more installation space. But yeah, look, we just have empty slots, and you can also see it looks like there's a gold-plated PC board all the way across the bottom, forming basically the EMI can on the bottom. Also, you can see this. So this is just a gasket, so that when you screw these down, you get a very good electrical connection between this and that, and therefore they, there's no leakage. Because actually, basically a long narrow slot where the slot is a function of the wavelength can actually turn into a pretty effective radiator. So you have to make sure that your slots are all sealed with, very well. Otherwise you can wind up with RF leaking through, extremely small slots, because the length of the slot plays a big factor in how much it radiates, rather than actually the width or any other factors. There's actually an antenna that's composed basically of a waveguide with slots cut into it. I don't remember what it's called. I've just seen pictures of it. It's pretty wild. So let me just put the screws back into here. May not be apparent, but I just changed benches. So I have to remember that this little metal reinforcement bracket is between these two bones and these two sections, and this is A8 and A9. So this is on A8 and A9. So one thing you might have noticed when I had this cover off is that this appears to be built up by, they have like a single wide extrusion, and then they stack them together to make multiple, or to make the longer enclosure. So, oops. Actually, if we look at the side, you can see how each segment is its own little metal housing, and they're all just layered up. Let's look at the first thing over here, which is the crystal filter. Oh boy. So what do we have here? We have lots of discretes, and we have something huge in a can. Okay, so that can is EMI shielding, presumably for the crystal. You can see here in the bottom we have a few parts under there. This is fairly interesting. So you can see here our 19.9 megahertz in is going through a little transistor, and this is floating, and then there's that transformer, excuse me, not a transistor, transformer to isolate it. There's a number of little additional oddments here, like, what is that? It looks like a, oh, I know what that is. So that's, okay, that's awesome. That's a scope probe test point. That's really cool. So I guess, well, of course, because you'd be probing this with like high frequency scope probes. So the idea is, sorry, I had to grab a probe. So here's your probe. So the idea is the probe inserts into it, and then obviously it's not designed for this probe, but the idea is your metal housing connects with this pentagonal box, and then the actual tip goes into the hole. So that's a way of basically giving you a scope probe coaxial connection right into the circuit board. That's pretty neat, actually. I'll have to remember that, because I need it. I wonder where you get these little metal things. They may not be easy to get hold of. So other than that, we have, metal shielding can, which I'm not going to take off. And then just test points. You can see here this is labeled IF mixer. And then it looks like it's mostly ground. It wouldn't surprise me if basically the entire input of this was just, yeah, you can see literally they have ground, not connected, and then they just have these two tabs here, which I would imagine are probably just positive and negative rails, and you can see they're duplicated on the other side. So I would bet that this, basically most of these modules just rely on the backplane for power only. And then you can see, I bet this is like an HC49 crystal, or maybe a slightly larger package that looks like about the right spacing. You can see power comes in. It appears to only be a 2-layer board, which is fairly impressive. Though it also there aren't a lot of active components on here. And it's all discrete too. You can see here's power comes in, and it looks like it runs to these capacitors. This is probably an input filter. And then we just have transistors, more transistors. That's a bigger transistor. Wait, here's one IC in a hermetic package. There's a couple little transformers, resistors. Here are those interesting, like 2-pin dual in-line package ceramic capacitors. Those are kind of unusual. You can also see there's a hole there. I'm not sure what for. The only thing relevant is these two test points, and I don't know what they do with them. The transistor here, this is a 2N5109 made by Motorola. That is a 2N5178, I think. This is of an era where I'd expect the schematics are still available. So that wasn't too interesting, mostly because the thing that I think I'd most want to look at is in a can that I can't really remove. We'll just plop that back into place. I expect this to basically be identical. Yeah, so this is basically identical. It's the exact same board. They just have two of them. So this is the test reference Iaf amplifier. So now we get interesting. We have a lot of DIL parts, and then there's that really strange can thing here, which has it's got 4 or 5 pins. It's got 5 pins. It could be something obscure like a dielectric oscillator. I don't think so, because those are normally extremely high frequency. I've only seen them in like RF stuff. It's probably just an inductor, like shielded in a mu metal can or something. Other than that, we have there's a big capacitor. That's 0.01 microfarads, 1%. So this is like a high precision film capacitor. It's just interesting how long it is. The aspect ratio is interesting. And then we have, so these are all labeled 100 kilohertz. So I wonder if these are like 3 separate line driver chains, and then these all output the same thing. This is labeled test. We've got that's a IC with a little one of these heatsink fins on it. And then there's just a bunch of various P8512, P8512. What is this? This is 7400 series logic. 74 LS241, 74 LS194. Some national semi stuff. 74 LS00. I think that's an OR gate or an NAND gate. And then there's some custom stuff. We have lots of little ceramic dip caps, and there's an inductor. So one thing of note here is, again, it looks like, well, I guess they do have a few. It looks like they may be using a few control signals here. But other than that, it looks like this central section. Oh wait, no, they're using a whole lot of control signals. But it looks like, again, these kind of the 2 outer tabs and the 2 tabs in the center are, those are all power, I would imagine. The only thing really interesting here is this, and the fact that this is another gold-plated board, which is a 100 kilohertz Iaf amplifier. Lots of transistors. So next up we have, this is a A11 B1 Iaf mixer. B1 100 kilohertz, 19 megahertz. Okay. So this is just, it's another one of those boards. It's the exact same thing. Looks like we have the can thing in the same place. I wonder how many of those they have. I guess, you know, these things are good for, this is part of like a vector network analyzer, so you need, it has 4, it does S11, S12, S21, and S22. So I'll confess I don't really understand how they work, so maybe they need 4 IF stages for each of the signals. Here's another, yeah, okay, so these are identical. This is another A10, A12, so you can see these two. This is A10, A12, this is A10, A12. So we have A9 and A. I wonder what the difference between these two is. I mean, it looks like that pin isn't used there. There may be some minor part variances between these two that I haven't been able to make out. Oh, also interesting is you can see there are 3 holes there, and it appears there are corresponding holes in the metal can. So I guess there's adjustments in there or something along those lines. But other than that, they all pretty much look the same. This is an 8224 or 2442-45 mixer. Nothing to see here. Sorry. That's just a little bit. So what we have here, this is a 19.9 megahertz local oscillator generator. So this is quite interesting. So this looks like we have 4 outputs, PLS cal, and then there's 20 megahertz here. So I wonder if this is like a fractional, it takes 20 megahertz in and it gives you 19.9 megahertz out. That's kind of strange. But we definitely have some very interesting components. We have this, which is labeled 19.900 megahertz. I suspect this may be, it's either like a surface acoustic wave thing or an extremely high precision quartz crystal. Though from the fact that it's labeled 19.9 megahertz, I guess it's a crystal. And then these are probably, well, first of all, we have, obviously it looks like that's been hand gooped. It's got flux goo all over it. But we can see that the terminals of these crystals, the 2 terminals of whatever this device are, go right into those 2 devices. These 2 unnamed boxes. Which makes me think they may be like some sort of exotic inductor or something like that. This could be just a plain old inductor in a mu metal cover shield again, which would kind of be supported by the fact that it looks like there are only 2 pins inside the housing. Well, it's either 2, oh, no wait, there's 1, 2, 3, 4, 5. Yeah, I would guess it's a transformer of some sort, now that I think about it. You can see the interesting layout. This is a combination of really old school, it's old school, really early computer layout with a side of manual routing for stuff like that right there. Made in the USA. It's gold plated on this side again. More Hewlett Packard proprietary. No, this is a 7.4 LS390. Some more little hand wound inductors. You can see some more hand wound transistors or transformers. Sorry, that's just an inductor. It's only got 2 pins. And then we have a bunch of transistors out here, which I still strongly suspect are basically output drivers, like Class C or something. More of these little BNC test points. Or not BNC, excuse me, scope probe test points. Moving on. So here we have a test/reference sync detector. So here we have, ooh, interesting. So we have 4, it looks like specialty pot core transformers with, I believe, adjustable slugs on the inside. Though, correction, those are not transformers, they are pot core inductors, because each of them only has 2 connected, or 2 leads coming out of them. So we have a bunch of specialty inductors, bunch of specialty devices. It looks like this is actually, my guess would be this is a PAL of some sort, though it appears the sticker, well, it'll come off. You can also see we have, this is kind of interesting, like this right angle connector has an exposed lead, whereas the ones, well, I guess that makes sense. Iaf input, X output, Y output, and this is labeled 4 megahertz. Yeah, 4 megahertz local oscillator. Yeah, test X, test Y, 100 kilohertz IF. So my guess is this is a PAL of some sort. TPB28L22J 8501AF Taiwan, Texas Instruments. So I'm betting, my money's on that being a PAL or something along those lines, some sort of configurable logic, because otherwise they wouldn't have put a sticker on it. So this is actually labeled synchronous detector, which is very interesting. It makes me think this may be some form of lock-in. So So it wouldn't surprise me if this is basically like a very obscure specialty lock-in amplifier. You know, for basically detecting really low-level signals. We've got more of these. Those are wet slug tants, just from the fact that they've got glass encapsulation at one end. Some really specialty. These are all SIR-DIP packages. These two here as well. And then there's a couple hermetic CAN ICs at the end down here, and that's about it. Oh, I see why this is hard to get in now. It's because the screws and the pins of the IC are like catching on the metal shielding. So now here we have, this is A6 clock. And then we have another test reference sync detector. So this is apparently the clock. So all I see in here is a 20 megahertz crystal. So that is 20.000000 marked. So I guess that's a 20 megahertz ultra high fancy pants precision crystal. So on the output, actually up here, yeah, you can see we have 100 kilohertz cal, external reference, 10 megahertz clock, 4 megahertz local oscillator, 4 megahertz local oscillator. And then I believe all of these outputs are all 20 megahertz because that seems to be what they say. And then you can actually see here we have a little tine going to the freak, and then there's actually a pot. There's a many-turn pot down in here, so I would bet that that is like extremely fine tuning of the frequency. You can see we have more wet slug tants. That's actually the same part number. Whatever that is, they use in a bunch of places. Here's a Signetics part. It's just, I would bet that's related to the, actually, I'm not, crystal pins go into there. So I would guess that's related to, I would guess this is the actual oscillator chip, but it's not connected kind of directly in the way I normally expect. A bunch of 7400 series logic, some resistor arrays. Look at those interesting flat-ended resistors. See a little choke. And we just have big CAN transistors, a couple of these little test points. That's about it. Okay, I'm going to put this half back together and then we'll look at the other half. Hi. Alright, so there's just the, that's a lot of cables. So we just look over here. So I'm actually going to pull this out because this is interesting. So this is the, this ribbon cable interfaces with the controller module. So I expect there to be some ADCs and some DACs and some crap like that in here somewhere. I'm not sure if they're going to be on here. So this has one of these neat, like little spinny pull-out handles that they had in the controller module as well. And yeah, so here we have the Hewlett Packard processor interface board, which is just, well, there's some Signetics parts. It looks like it's a big binary, big, fairly wide bus. We have a fuse, interestingly enough, which makes me wonder if power is coming across, like some 5-volt logic power comes across there. It's a strange place for the fuse. But this all looks a lot like a... No, okay, so this is A to D converter, sample and hold, remote applications, pre-tune control. So it looks like the A to D is somewhere in here, so we'll get there in a second. So I would bet that this is just like line drivers and buffers. So we have 74LS245, 74LS245, 74LS373. I think that's a Signetics part. 74LS20, and for LS139. So just 7400 series logic and some obscure stuff. This is national. So that'll just plop back in there. I really like these like spin out grabby handles. They're really quite nice. Alright, that goes there, and then this big ribbon cable just plops back in there. It looks like this is a 30-pin cable. So this is the main phase lock. Oh my. Oh, fuck, the RF gasket's caught. Alright. So what do we have here? We have a chip with one of those clip-on chip heatsinks, which is kind of amusing. The main device here is this, which is a QCG7610. Also by, I think that's Signetics. Canned IC. Here's some big film caps. Test points. So our inputs here are Vto tune. It's not focusing. Vto tune 20 megahertz and PLL IF, and then you have holes here for. I'm not actually sure what those holes are for because you can't really get to that test point over this big heatsink. They may be actually for ventilation because this is pretty sealed. Another thing we can see here is you can see how these aluminium sections stack together to form the cage. And it's all dusty in it. So this, I can't get that heatsink off easily. But yeah, so that's just one of the, it just clips on. You can still buy those, actually. What is this device? That is an H8752 from National, but it's canned. I don't know what it is. We have, more caps. It's labeled main phase lock. You can see this is also all gold plated. SIRDIP stuff. Here's some 7400 series logic. 74LS33, 74LS74. That's a flip flop, I think. But yeah, not much luck there. I mean, just interesting. Some big cap. There's some more tants. Cool stuff. Yeah, this is 2%, and that's a 1%. That little small one down there. So these might be part of like the loop. I'm not sure. I don't know where the actual oscillator is on this board. Well, I mean, let's see. So our signal comes in here, and then it runs into this. So I think this is the actual PLL device because your 20 megahertz comes in here and then runs right to that chip, and your IF comes in and also runs right to that chip. So I would imagine this is probably like the actual PLL device, so I'm not too sure. And then some of the other stuff may just be like a programmable divide down to control it or something like that, I'm not sure. Anyways. Actually, that's something I didn't notice. Or I didn't point out. Look at this. We have a... that's quite something. So this blue box here, if it'll focus, is a 14 meg 2% resistor. 14 mega ohms by KDI. So I wonder what they need 14 megs for. But as you can see, it's going into one terminal of that capacitor. So this is probably like a just a redonkulously long time constant something. All right, next up is this here, which is labeled pre-tuned control. So this has another heatsink IC where I'm not going to be able to get the heatsink off, that's a pain in the ass. And then we just have 7400 series, these are AMD SerDip parts. 8502 DPP, 8502, these are the same. Looks like these are all bused together. 74LS273, 74LS273. You can see some interesting, you can look at how they've got these cuts in this ground plane area here. I wonder if they're controlling currents. It looks like these two inputs here, I would assume, are connected to this device, which is sitting on its own little floating ground region. And then it looks like they have, I would guess those are actually in, assuming they're bridging the gap, yeah, they are. I would imagine that these are probably series inductors, so they have this little floating section that can be bobble around in common with regard to common mode. Other than that, it's just 7400 series, just unexciting 7400 series. This is a 200 volt 0.056 10% capacitor. I wonder what they need a 200 volt cap there for. Other than that, it's just resistors and 7400 series logic, and then these interesting custom marked devices. Don't really want to disturb. I can't get it off because it hits that freaking resistor. I don't want to damage it. But it's interesting that they have ICs that they felt needed that little extra thermal kind of help. So this is Vto Input and this is test VTO, and it looks like this is just connected together with this input through a resistor. So I'd imagine this is just like a protected tap-off. Carrying on, we have this, which is labeled Iaf Counter. So here we just have we have 20 megahertz, A1 and A2 20 megahertz. I wonder what the functional difference between those two is. That in fact may be outputs now that I think about it. Then we have PLL IF and we have analog out, and then there's a little LED that says IF present. And I don't really see, all of these are custom parts except for some 7400 series logic. There's lots of custom stuff in here. But I don't really see anything recognizable. One thing of interest here is if you look at all of these pin headers, I wonder if this is like a test header. So I'd imagine there's some extremely high-speed divide downs in here or something to that effect. It's interesting that it has IF in and analog out. So I wonder if this is like a voltage to frequency converter or something. You have analog out and IF in. So this should be interesting. This is labeled sweep ADC, which makes me think this is probably driving a VCO of some sort. Right. Come here, you. So in here we have lots of logic. Trigger in, sweep in. Sweep in comes in here. I don't actually see the ADC. Though you can definitely see down here. This may be in like a dual slope type affair. Because actually, if you look here, you can see we have a some stuff wrapped in a guard ring. So they may be, and in fact, one end of that goes into this 0.33 microfarad, 2%. So one end of this actually goes into this 0.33 microfarad minus 2% film capacitor here. So that may be like the integrator for a dual slope or a integrating ADC. It wouldn't surprise me. I think this is about the right vintage. One thing of interest is you can actually see that we have a test point that's actually accessible through the test point hole. TP1, and then right there is TP1. You can actually reasonably get to that. And we just have 74 series logic, 74 series logic, and then specialty stuff. That is by the trigger in. So this is the trigger input, which looks to run. It actually goes this way and it comes to this device. And the rest of it's just random 7400 series logic. So I would imagine that this section here forms the ADC. You've got a canned IC. That's interesting. So look here. So you see these two, that 6-pin pattern there. So that's just in one can. So I bet those are like some extremely closely matched, thermally coupled transistors or JFETs or something along those lines. Those are quite interesting. These are hard to buy these days, incidentally. Actually, we have another one right here. So that device also has 6 leads. So that's another pair of matched transistors. That's quite intriguing. So I would bet that this is some fairly complicated homemade analog to digital converter, like a discrete ADC. Is there a date on here? I don't see a date. But this is board A20. So next up is this board, which is labeled ADC Control. So my guess would be that if we have like an integrating ADC, that there's probably a counter in here which takes, and then this has the actual like the comparators and stuff. So this does the actual integrating for the ADC. We'll see if I'm right. So this is straight up all logic. So, well, that's interesting, except we do have a fuse up here, which is the pulse. I think that's, yeah, so that fuse is in series with this pulse DR output, which my guess would be pulse duration. And then our 10 megahertz clock comes in and runs all sorts of places. But yeah, so we have 74LS390, 74LS157, LS174, 74LS00, 174, 00. Yeah, oh, hey, here's another fuse. Oh, wow, yeah, this is extremely typical of the time and something I wish they would do these days. You know what this here is? That's a spare fuse. Because manufacturers those in, you know, of this era were amazing. So this is 125 volts, 3/10 of an amp fuse. So right in there is an extra fuse, so when you blow that fuse you still have something to go off. Then we have 2 test points, which are again actually accessible this time. So my guess would be that this is just a straight up like a counter. We have another CPLD. So I would imagine that what happens here is you just have like, this is I would bet the bus is like 8 bits, and then I bet this is like a 16-bit or even more bit counter. So what they do is they integrate. They have a big, huge cascaded ripple counter, and they integrate up until the trigger comes in, at which point they gate the clock, and then they read it out in banks or something along those lines. You can see it's labeled ADC Control. We have another one of these little ferrite inductors and a big tant. And then you can see these are actually the 0.1 microfarad, or somewhere about there. They might be, well, they're 104, so they are 0.1 microfarads. Just logic bypass, and you can see these vertical rails of the logic power. And then you can see on the bottom side the routing is all horizontal, so this is typical vertical on one side, horizontal on the other side routing. This is very typical of logic. So interestingly enough, we actually have, this is labeled sweep ADC, this is labeled ADC control, and this is labeled AD converter. So I'm not too sure what's going on here. There may be two ADCs. It's strange that they call this one A/D and they call this one ADC, which is why I'm kind of grouping these two just in assumption, because I would assume that the ADC things go together and the A to D thing is probably a separate thing. Let's actually see what's in here. So this is, actually, I don't remember where this connected to. This is A18. I'll have to go through the cables while I'm putting it back together. Oh, hello. So there is one interesting old ass part, and it looks like shit's growing on the thermal clamp. Oh no, that's foam. So what we have here is one old ass ADC, which appears to be thermally clamped to this faceplate. Actually, so there is some very decrepit foam under there. And there is heatsink goo all over the screw threads. At least it looks like this is coming apart. Oh yeah. Hello, era. So what we have here is a custom brand. In this case, it looks like they were subsumed into Intersil, but this is a very old, very custom, probably a hybrid ADC converter. Get a little bit of ISO. Where did my Q-tips go? I'll just use some paper towel. So what we have here is a Daytel Intersil A to D converter, ADC-HZ12BMC. So my guess would be that this is probably a 12-bit ADC in a really old school, like a hybrid package. And then it appears they're actually, the thermal clamping is mostly on the bottom side. Yeah, so it looks like they're heat sinking it from the bottom, which is interesting. So I would imagine that what we have here is input buffer, ADC control logic, and maybe staging. Because if this is 12 bits, they'd probably need to read it out into 8-byte chunks. I'm not sure how it works. I'm not going to actually pull this out of the socket. I don't see any reason to do so. But that's quite interesting. So there's quite the legacy curiosity. I mean, that's been replaced. You know, I mean, this was probably hundreds of dollars at the time. I know that I worked, you know, some of the projects at the lab I've done, you know, back in like the early 90s had like a 14-bit monolithic ADC for an experimental astronomical CCD camera that was, it was like a $900 chip. You know, just because it was a megasample per second at the point where you were using like DOS. And they had to write custom software to talk to the thing and everything, just because, you know, at that point a megasample per second at 14 bits was, you know, just an inordinate amount of resolution. Yeah, it's interesting that it apparently needs to be heat sunk. And they've got this custom machined little aluminium brace to hold it. Made in the USA by Daytel Intersil. It's a cool bit of history right there. You don't see those anymore, and you can see it's like a hybrid ceramic package with leads coming off the bottom. And then obviously this was like a clamp that holds it together with a whole bunch of foam, or there's some foam that holds pressure on it that's been degrading and should really probably be replaced, but I'm not going to do that today. The worst thing, you know, the thing about that is that these instruments, these VNAs, are still really, really amazingly decent quality. Okay, yeah, that's not clamping at all. So that could be part of the problem, why this was thrown away. Because if you look, you can see that there's no clamping force there because the foam has decayed. Yeah, actually, if you look at the slope there, and then this is presumably supposed to be more like that. So maybe the ADC overheated and self-destructed or something. Or maybe it just was inaccurate. Didn't I have a little square of self-adhesive? No, I don't. Bother. Okay, well, I'll let the guy who I'm giving this to know about that. But other than that, yeah, it's just 7400 series 74LS244. There's an interesting AM25LO2. It sounds like an EEPROM, but I doubt it. Oh, yeah. Actually, while I'm on the topic of this card, oh, they aren't loose, they just are sticking out. So here we have a sample and hold, which I would almost guarantee probably goes from here. I would almost guarantee that this output here plugs right into the ADC. So, here's another interesting board. So I would actually guess that these are the 4 hold capacitors, because film capacitors like that are kind of typical. I bet this is gating. This is an interesting part. PMI 8404. That may be like an analog switch of some sort. So our output. So yeah, okay. So here's the coax output. It runs to that pin there, and then over there. So I would imagine that this is probably like a buffer op amp or line driver, U10, and then that couples into this device, which I would imagine then, oh yeah, so here we are. Look at that, we have 4 guard ringed little traces, each of which is on one end of those capacitors. So those are your 4 hold areas right there. So they're guard ringed to prevent surface creepage across the board, or surface leakage across the board, excuse me. It's interesting that we have, so there's test X, test Y, ref X, and ref Y. I wonder if that's device test X and Y and reference X and Y. So this may be part of like the network analyzer where it's sampling, the 4 different parameters of the system. Though I am so massively talking out my ass, you should just ignore me because I don't really understand RF. You can see here we have scope probe connections, and you can see we have these 4 inputs, and then there's the just ref X, ref Y, test X, test Y, and then we have sample and hold out, which is J5. It goes through that device, and then there's just some other stuff. Some more AMD parts, 7400 series logic, which is probably just onboard buffering for all your control stuff. And then we're down to the last board here, folks. This is the A16 remote applications. We have Vto tune-in, FM out, and that's it. Ha! So there is not much in here. Look at that. Actually, that's interesting. Look at these copper sections here. I wonder what those are for. I guess they might just be copper fill. But yeah, so we just have these 2. Vto tune-in comes in here, FM goes out there. And then they just run to this single IC, which is a PMI 8752. So I have no idea what this does, but it's certainly Spartan. It only uses power. So you can see we're only connected to the center 4 pins at all. So whatever this board does, it does exclusively using these 2 inputs and outputs. It's kind of a letdown. So other stuff in here, down in the front panel here is just a front panel interface. This is just decoding logic for the buttons on the front panel. We also have down there, this is just so they run AC mains through that cable over to this point, switch it, and then run it back to the power supply. The power supply itself is over here. I'm not going to take this cover off. There's just fuses and some old-ass rectifier diodes down there. And then there's just these absolutely enormous Sprague Powerlytic 45,000 microfarad. Wow. 45 millifarad capacitors. And then you just have lots and lots of BNC crap on the back, which is what all this yellow cable is. Alright, so there you go. I'm just going to plug it back together. So this was actually quite interesting. You can see here we actually have an SMBT. Actually, I need to put the screws back in first. Alright. So I just realized I haven't actually powered this up without the lid on, just to make sure all the status LEDs come up. So, so yeah, it looks like it comes up fine. Plus 15, negative 15, plus 5, minus 5. Wasn't there a status indicator LED here? Yeah, IF present. I guess it's not finding the IF. It might have to be turned on. It wouldn't surprise me. But it looks like the power supply works. It's not in thermal shutdown. And then there's actually a whole pile of LEDs down here too, which I would assume are also power related. So cool beans. So that's the interior of the Hewlett Packard network analyzer, which is an 8510B. Actually, I can't do anything. All the LEDs on the front panel that tell you which channel is on are both illuminated, and doesn't tell me much. So I guess the front display panel probably does nothing without a computer present. Anyways, I hope you found this interesting, and yeah, stuff.